In this lesson, we're going to learn how to find the area between two curves. So in the previous lesson, we learned about finding the area under a curve, which means we're looking for the space between the curve or the function and the x-axis over a specific interval. So this is what we were talking about last lesson. So that pink shaded area is between the function and the x-axis over a certain interval. But now in this lesson, we're going to find the area between two curves. So we're going to be looking for the space between those two curves on the graph on a specific interval. That's what this looks like here. So looking at this graph, we have this function in green, and then we have another function in pink. If I look at that interval from 0 to 5, I'm looking for the space between the two functions. So here's an example of what we're going to do. So looking at the graph on the left where it has pink area and green area, and we have a pink curve and a green curve. And if we want to find the area trapped between those two curves on the interval from 0 to 3.5, what we're going to do is we're going to integrate, but we're going to integrate by finding the first function minus the second function. The first function will always be the upper curve, and the second curve will always be the lower curve. So looking at it conceptually, what we have is this area here, and it's above the x-axis, so it's we'll approximate it at 9.31. That's this here. And then we're going to subtract the area in the green. Now, because the area in the green is below the x-axis, that's going to give us a negative number. And if we round it, we get negative 5.5. So that's here. Now, because we're taking the area under the curve for the pink curve, and we subtract the area under the curve for the green function, we're going to take 9.31, which is our approximation, and then subtract a negative 5.5. Because we have a double negative here, it's going to end up being added together. So when we take this area in the pink and subtract it from this area, we end up getting the area as 14.81. Now, when we look at it as the total area without being split up into different areas, that total area will be 14 point, and then again, if we round, 81. So area 3 is the total area between the curves from 0 to 3.5. So in the previous example, I showed you how you find the area between two curves when they're on opposite sides of the x-axis. And it worked out because we subtract a double negative, which means it adds the two areas together. Now, what happens if they're on the same side of the x-axis? So when we find the area of the green function, you've got to remember that the whole area goes all the way down to the x-axis. You've got to find the area between the curve and the x-axis. So it's all of this. And then we're going to subtract the lower curve, or the area of the lower curve. And the area of the lower curve is this area here in pink. So it overlaps with the green. Now, if we use the same rule where we take the area of the upper curve and we subtract the area of the lower curve, notice it works out again. So if I take the whole entire green area, which is 20.72 when we round it, and I subtract the entire red area, that's going to be 9.04 when we round it, we're going to get a total area of 11.68. Now, because the red area is not below the x-axis, we're actually subtracting positive area. So we're getting rid of this red area and just keeping what's in between, which looks like this. So this area in between the two curves is 11.68. So here's our first example where we're going to work through with specific functions rather than generic ones. We have f of x, which is the line 2x plus 5, and that's the line that's highlighted in blue. And then we have a quadratic, x squared minus 8x plus 21. That's the function in green. We're going to find the area between those two curves, f of x and g of x, on the interval from 2 to 5. So that's the area that's shaded in the pink. Now, because on the interval from 2 to 5, the blue function, which is your linear function, is above the green function or the quadratic, we have to list, when we do our subtraction, we have to put our linear function first. So I have the linear function f of x minus g of x, which is your quadratic, and we're going to integrate that from 2 to 5. First, let's clean it up a little bit to make it easier. So you need to distribute that minus sign to all the terms in g of x. And then when you combine like terms, you get negative x squared plus 10x minus 16. And again, we're going to integrate that from 2 to 5. When we find the antiderivative, we're going to get negative x to the third over 3 plus 5x squared minus 16x. And then when we evaluate it, and we put 5 in first and subtract what we get when we evaluate it at 2, we're going to get 18 as our final answer. In this second example, we're going to do the same thing as example 1 in practice. We have a function f of x is equal to x squared minus 6x plus 10. And that's the function in the blue. We have the function g of x is equal to minus x squared plus 8x minus 10. That's our function in green. And we want to find the area on the interval from 3 to 4 that is trapped between those two functions. That's the pink area. Now, because we're finding area between two curves, we need to take one curve and subtract the other. But it's very important to look to see which is the upper curve, because that needs to go first. So the blue function, the f of x, is the lower curve when we're looking at the interval from 3 to 4. The upper curve on the interval from 3 to 4 is the green function, which is g of x. So we're going to integrate this from 3 to 4. And we're going to take g of x minus f of x. Before we integrate, I personally find it easier if we combine like terms first. So what I did is I distributed that minus 6 in front of the second parentheses, and then I combined like terms. And I got the integral from 3 to 4 of negative 2x squared plus 14x minus 20. Now, when we find the antiderivative, we get negative 2x to the third divided by 3 plus 7x squared minus 20x. When we evaluate that at 4, we get a negative 32 over 3. And then when we evaluate that at 3, we get a negative 15. So we're going to have a double negative there. So that's going to end up giving us, when we combine those and take care of that double negative, we're going to get a final answer of 13 over 3. Example 3 is a little bit different than example 1 and 2. For this example, we're going to find the total area that's bounded by the two functions, f of x and g of x. So our first function is negative x squared plus 4x plus 63. Our second function is g of x is equal to x squared plus 12x plus 39. So we're looking for the area that's in the pink, like the area that's trapped between those two functions. Now, we don't know what these points are here that I highlighted in yellow, because we need to know what those are, where those intersection points are, because that's the interval that we need to integrate over. So first we need to find those intersection points. So what we need to do is set those two functions equal to each other and then solve for x. And then when I moved everything to one side and set it equal to 0, I got 2x squared plus 8x minus 24. And that's a quadratic, so we can use complete the square, quadratic formula, factoring, whatever you want to use to solve that quadratic. And then once you solve it, you should get that x is -6 and x is 2. So that's those two yellow points on the graph. That's where those two functions intersect. So it traps that area between the two functions. So now we know that interval that we need to integrate over. So now this is where we integrate. Because that interval goes from -6 to 2, that's how I'm going to set up my limits on the integral. Now, looking at the picture on that interval in which the area is bounded, you'll see that the blue function, which is the f of x, is on top. So I'm going to use that function first and then subtract the g of x. So I have -x squared plus 4x plus 63. That's the f of x, and then I subtract g of x, which is x squared plus 12x plus 39. So before I integrate, I want to clean that difference up so that we can combine like terms and make things a little bit easier. So I've got to remember to distribute that minus in front of the g of x. And then once I do that and I combine my like terms, I'm going to get -2x squared minus 8x plus 24. So that's what we're going to integrate from -6 to 2. When I find the antiderivative, I'm going to get -2x to the third over 2 minus 4x squared plus 24x. Now I've got to evaluate that from -6 to 2. When I plug in 2 into our antiderivative, we get 80 over 3. And then when I plug -6 into the antiderivative, we get -144. Because of that double negative, we're going to end up getting 80 over 3 plus 144. And then the final total area between those two curves would be 512 divided by 3. In example 4, we are going to find the area bounded by these two curves, f of x and g of x. And this is going to be very similar to example 3, only in this one there's a little bit of a twist to it. So when you want to find the area between two curves over an interval, sometimes you have to split the interval into subintervals, and this is because the upper and the lower functions might switch within the overall interval. So notice here that in the interval from 0 to 4, g of x, which is the line, is on top. And then in the interval from -4 to 0, f of x is on top. When you find the area between two curves, you have to have just one function as the upper function when you integrate. So what we're going to do is we're going to split these two areas up into two different integrals and then just add them together. So our f of x is x cubed minus 10x plus 25, and the g of x, which is the line, is 6x plus 25. I put the shaded areas in there so that when we're evaluating the two different intervals, we can keep track of which one is which. So notice this yellow area here. That's going to match with this integral that I highlighted with the yellow brackets. Now, we're looking at the whole interval from -4 to 4 because we want to get the total area that's bounded by those two curves. However, From -4 to 0, we notice that, let's see, that's f of x is on top. So we need to set up a separate integral for the yellow area, because then when you look at the blue area, the line is on top. We can only have one upper function on each interval. So we're breaking it up into smaller intervals, and then we just add those areas together. So we're going to evaluate the integral from -4 to 0. And I took f of x, that's right here, the cubic, minus the line, because we're on the yellow interval here. Now looking at the blue interval, the line is on top. So that's why we're creating a different integral for this area. So for the blue area, we're going to evaluate that from 0 to 4. And now on this interval, the line is on top, so the line is going to come first. So here's g of x minus f of x. When you find the antiderivative of the yellow area, we get x to the 4th over 4 minus 8x squared. Then for the blue area, we're going to get an antiderivative of 8x squared minus x to the 4th all over 4. I did an intermediate step where I combined this first before I integrated. So just so you're aware that that's where these values are coming from. Okay, when I evaluate the yellow area, I get 64. When I evaluate the blue area, I get 64, which makes sense that they're the same because they're both above the x-axis, so they're both positive, and it's symmetric, so each one should be the same. When we add that up, we get an area of 128. In our last example, we're going to work through a business application. So we have this graph here. We have the cost function right here. It's labeled c of x. That's the lower function. And then the r of x, that's the revenue, and that's the upper function. The x-axis is in years, and the y-axis is in dollars in the thousands. So this 250 represents 250,000. What we're going to do is we're going to project the profit for the next 10 years. Now, in order to find profit, we need the revenue and we need the cost. So our revenue function is 80 times e to the 0.1x. Our cost function is 0.9x squared plus 70. Now, if I take the revenue minus the cost at a certain point, it will give me at a certain year what is the profit. But we want to know the accumulative profit over the whole 10 years we're going to have. And that profit is the difference between the revenue and the cost function. We are going to integrate using the limits 0 to 10 because we want to project it for the next 10 years. And we're going to take our revenue function, which is 80 times e to the point x, and we're going to subtract 0.9x squared and 70. This minus right here comes from the fact that when I subtract the cost function, I subtract both terms. So both of these are negated. So this is why we have a minus here. When we find the antiderivative, we're going to get 800 e to the point x minus 3x to, oh, that's a 0.3, minus 0.3x cubed minus 70x. Now we're going to evaluate it from 0 to 10. When I plug 10 in first, I got to take whatever I get for 10 and subtract whatever I get for 0. So when I plug 10 in to the first term, so I'm looking at 800 times e to the 0.1x. When I take 0.1 and I multiply it by 10, we're just going to get 1. So now for the first term, when we evaluated a 10, we're going to get 800 times e. When I plug in 10 for the second term, I have to cube 10 and then multiply by 0.3. And then when I plug in 10 into the last term, I get negative 700. Now we're going to subtract whatever we get when we plug in 0. Well, if I plug in 0 to the second and third terms, those are just going to disappear because we have 0 times 0.3 and 70 times 0. When I plug in 0 here, though, I'm going to get 0 for the exponent, and we know that e to the 0 is equal to 1, and then I take that 1 and multiply it by 800. So when we evaluate it at 0, all we get is that 800. So now we get the answer of 374.625. So 374.625 isn't quite our final answer yet. We've got one small thing to do. Remember what the y-axis represented? That was the dollars and thousands. So this isn't $374. This is 374,000. So when we move that decimal place 3 places to the right, so that we get it in thousands, we get 374,625 is what we project for the profit in the next 10 years. So to summarize this lesson, there are 3 major takeaways. The first one, if you want to find an area bounded by 2 curves, f and g, on an interval, so you're going from like a to b, you want to evaluate the integral with the limits from a to b, where you take the top function, f of x, minus the bottom function, g of x. Okay, when you are trying to find the entire area that's bounded, you need to find the intersection points first so you can see where the area that's enclosed starts and stops. So when you're trying to find the entire area, you need to find the intersection points first, and then you evaluate the integral of f of x minus g of x, and whatever your intersection point is bigger, that's going to be your upper limit. And whichever intersection point is smaller, that will be your lower limit. One last thing to mention. If you're looking for the area bounded between 2 curves where the top and bottom function get swapped, you need to create subintervals so that each subinterval only has one function as the top and one function as the bottom. And that way you can integrate each of those subintervals and just add them together to get the total area.